Good morning. My name is Arndt Offinger, GKN Aerospace, and I have a presentation for you today on thermoplastic composite ribs for wings. And this is a development we have done for the Wing of Tomorrow project. GKN, as an introduction, is an aerospace supplier, one of the larger ones in the world, tier 1, and we have a strong focus on several businesses and 48 performance centers worldwide. We have a broad range of technologies, among them metals, structures development, and also composites, different types of composites. And we have 4 global R&D centers based in the UK, in Sweden. There will be one in the US, and we have a recently created one in the Netherlands as well. Thermoplastics has been a focus of our company for many, many years, and this diagram shows the growth of thermoplastics technology over the years. And currently, we are developing technology for large structural parts, heavily loaded parts, and among them are parts of wings, such as ribs, which we will be discussing today. Thermoplastic rib has recently been developed in the frame of the Wing of Tomorrow program with Airbus, partnership with Airbus. And this rib basically, if you look at it from a distance, it seems like a metal part, but basically it's a composite. And we have developed several technologies to make this a feasible solution for heavily loaded ribs in wings. But first, the use of composites in wings. If we look at wings, we see at the bottom of the wing access hatches, many access hatches, and these are used to inspect the wings on the inside. And this is particularly necessary when you're using metals. When transferring to composites, it becomes a possibility to leave out these hatches. And that's basically one of the drivers to go for a full composite wing. So not only the skins and the spars, but also the ribs. And so this has driven us as a partner in the Wing of Tomorrow to consider composites for wing ribs. The discussion was then, shall we go for thermoplastics or thermosets? And we chose to go the thermoplastic route to see how far we could go in part integration in making a composite part cost effective and suited for high rate production. And here we see the solution. The solution is a rib that is made in a so-called co-consolidation process, so a single-step process to melt everything together under pressure based on simple preforms. And the process is a sequence of events, so starting on the left with slitting, and then laminating, preforming, and most importantly, co-consolidating at the right bottom is to create the panel configuration or the rib configuration. We are doing this in our research center in the Netherlands. We are also cooperating with partners in several projects to develop the technology needed for this type of process and product development. The picture here shows the pilot line that was set up to manufacture the ribs for the Wing of Tomorrow. On the left is a tool. It's a modular tool with integrated heating and cooling. And in the middle, the blue press is a press that has pressure in 2 directions, horizontal and vertical, to apply pressure for this tool. So it's an out-of-autoclave process to melt together preforms at high pressure and high temperature to create a part. And this has to be a fairly fast process in order for it to be suited for high rate production. The Rivet Development, so like I said, one-shot co-consolidation. There are several features which I will explain in a moment. And this development was done in a corporate collaboration between our UK and Netherlands specialists in the area of design, manufacturing development, and automation. One of the features is for the stiffening of the vertical portion of the rib is the use of so-called butt-jointed stiffeners. So the stiffeners are connected to the vertical element, the web, purely by polymeric material with the short fibers. And this makes manufacturing very simple and also gives the designer a lot of freedom to design his product. picture on the right shows a detail of the stiffening elements with the polymeric material joining the stiffener to the vertical web. The second feature is at the bottom of the product. We have a flange going in two directions. So there are three basic elements for the rib that come together here, and also a so-called noodle to fill the triangular area here at the bottom of the product. When these preforms are co-consolidated, they create a very, very strong rib foot that can be loaded in tension and in compression at very high levels. In order to verify the quality and the performance of the concept, there was a subcomponent test program first, and we see some pictures here that show test subcomponents that have been instrumented, and several were manufactured, and they were loaded both in tension vertical and in compression vertical. And this next picture shows test setup. We used two laboratories within GKN Aerospace, one in the UK and one in the Netherlands, doing these tests, also comparing the performance of the different specimens. And what we saw is that the failure loads were well above ultimate, so we have some margin in the design as it was made and built for this program. So finally, this picture shows ribs. There were 3 ribs supplied to Airbus in the UK, and they will be used for testing and also for assembly into a full-scale outer wing torsion box. And this box will be tested. So the testing of the wing will also include the testing of the rib. So, and with this final slide, I would like to conclude my presentation. So in summary, we have been able to develop a thermoplastic composite rib for a wing of an Airbus aircraft in the Wing of Tomorrow program, showing the benefits of performance of this product, a very high strength. The weight is clearly a reduction as compared to aluminum, and the process time of less than an hour shows the potential to do very fast manufacturing, to be able to achieve the manufacturing rates needed for airliner programs, among them the narrow body programs. So all in all, a very successful development, and we are proud to have worked on this also with Airbus, and we will continue our development. Thank you very much. All right, so there are several questions which I will try to answer. First one, since it's out of autoclave, can you please tell me how you are controlling blowholes porosity? Yeah, so this is an out of autoclave process, but the tool, it encloses the product fully, and the tool is heated and cooled, and it's also compressed in 2 directions, in vertical and horizontal direction. So if you have the proper control of the tooling and of the heat up and especially the cooling sequence during the process, then you can guarantee the quality without the porosity occurring. Clean room requirements, no, they do not exist. There are no clean room requirements, typical for thermoplastics, because there is no out time. So we do it in a normal factory environment. We do dry the material before we put it into the process. So the preforms, when they go into the final consolidation step, we do dry the material in order to prevent moisture from coming out of the preform and spoiling the process. Are the 2D laminates made from UD tapes? Yes, they are. And which material? Okay, there are several materials available on the market. For this rib, we tested 2 materials. We worked with the Solvay APC2 PEC FC material, and also with the low melt peak tapes from Toray Advanced Composites. Have you been involved in the integration of the rib to the full box? Yes, of course. So the design of the rib was made by our design team in the UK, and they are part of the Wing of Tomorrow project, which is intertwined with Airbus, with the Airbus design team. So we're basically working with Airbus requirements and using this to design the rib. how has it been connected to the rest of the structure? Yeah, so the connection between the rib and the top cover, as it's called, and the bottom cover, the panels, is with bolts. So there are bolts going through the two flanges of the rib, the bottom flanges of the rib, and there are also bolts going through the top of the vertical web that connects the rib. And I'm not sure if I have a picture here of the bolts. Attachment, yes, you can see some holes here. Yes, here in this picture on the left, you can see holes in the flanges. So this is to attach to the bottom. Here are holes to attach to a stringer at the front of the torsion box, holes to attach to a stringer in the back, and then here also holes at the top of the rib to attach to vertical element that is part of the top skin or top cover. So let's see, any works for repair? Very good question. No, there is a lot more research to be done for repair. Repair of thermoplastics in theory, and that's the big goal we are hoping to achieve in the future, is by remelting the material. The issue is that when we melt a thermoplastic composite and we do not apply pressure, then we lose the consistency of the part. So today, as far as I'm aware, we don't yet have the true thermoplastic repair methods that we would like to have for this type of component. Repair today would be very much along the lines of conventional repair for composites, so scarfing and machining and then laminating or even bolting patches onto the rib. But there is potential for real thermoplastic repair, but that requires a lot of development. We have the TPRC Research Center in the Netherlands that is working on repair currently, but a lot of work still has to be done. How do you check the quality control of the ribs? What methods of NDT and control geometric parameters do you use? So for quality control, it's a conventional NDT, so phased array, C-scan, A-scan. These technologies all apply to this product and have been used extensively in the product development. Geometric parameters it's a conventional geometric measurement. So I hope that's helpful. Okay. Any more questions? And I think I was a bit late in starting my presentation, so my excuses for this. Thank you. I think I have a new question. Co-consolidation seems to be the crucial point. Could you provide some more explanations? So yes, the key of the process is indeed the co-consolidation step, because before the co-consolidation we have to make a preform, but that's not very critical. The quality of the preform is not as relevant as the final step. In the final step, basically what we are doing is we have tools that fully enclose the product, tool elements, and these tool elements have to be designed very well. They have to be very exact in shape, and they have to release the product once it's co-consolidated. And so we are taking the tool, we are loading it with preforms, and then in the press we are applying pressure in two directions and heating the tool to melt temperature, holding the melt temperature for a certain period of time, a couple of minutes, and then we are actively cooling back down to a release temperature. And when the release temperature is attained, the tool is basically opened and the part is removed. So you can see that there are stiffening elements on the vertical part of the rib, and the tool has to be such that when it's opened, that the part can be easily removed from the tool. So a lot of effort in the development of this product has been in the tool geometry, the tool features, and the tool design. So that's very critical to the success of this technology. Question. Sorry, maybe missed. Do you need to have special software for the simulation? Aurelio, that's a good one. Yes, we do use software to simulate the process, to speed up the development process and to reduce the amount of trials and the amount of tooling iterations. And yeah, that escapes my mind. I'm getting older, but what is the name of the software that we use? If I remember it, I'll mention it in a moment. But it's a standard software package that we use for thermal calculations. And basically, you model your tool and you model your product and the thermal process that's going on, and then you see how fast it goes. So yeah. How is the laying process coordinated with the forming process? What about the gap management or the fiber angle? Yes. So the layout process we do with an automatic tape layer, an ATL machine. And the ATL machine lays down material in 0-90 plus minus 45. The machine has an angular cut feature, so it can cut at 45 degrees or 90 degrees. And with this process, the blanks are made, which become the preforms. The two preforms for the vertical web and the preform at the bottom for the bottom flange. And the angles are tightly controlled in the ATL process. And then we have a preforming step, which is basically a very fast press cycle at low pressure. And in this press, there are pieces of equipment that are holding the blank to make sure that the angle of the blank versus the tool is correct. And then in a fast stamp forming cycle, there's the stamp forming of the preform. So the variation in angle is very, very small during the preforming process. And then in the co-consolidation cycle itself, nothing really happens with the material. It basically, the polymer becomes fluid. There is no real movement of fibers. There should not be. If the tool is correct, if it is fully enclosing the product. So the angles of the fibers stay as they are. So that's a fairly controlled process. Any other questions? Thank you. And by the way, hope to meet you all at JC next year in person. This is second best. Yeah. I'm pretty sure next year we will have a physical JC again. So thank you all very much for your interest, your attendance, and also your good questions. But if there's any other questions, I'm still here. Yeah, thank you for your positive feedback. Much appreciated. Okay. If there are no further questions, I'd like to close the session. So thank you very much, and see you all. Someone's asking here if, yeah, it's in Dutch even. Couldn't see the presentation. Could I see it somewhere? Yes, I've uploaded the presentation to the site of the GEC sessions or JEC sessions. So and this presentation is being recorded, so it should become available. But perhaps check with the JEC organizers. Thank you. Okay. So if there's no further questions, I would like to adjourn the session and truly thank you very much for your attendance. So thank you, and see you in the reels soon. Thank you.